Hello! I recently wrote some really tiny computer programs for an event called LoveByte. It's an annual online-only demo party. In case you've not heard of a demo party before, it's an event where programmers, musicians, and artists come together to show off things they've created. Normally, these creations are computer programs that render real-time animations or visual effects, often accompanied by music or sound effects. LoveByte specifically focuses on what you can do in that genre with a very limited program size. This kind of challenge is so common it has a name. It's called size coding. That appeals to me quite a bit, so I made a couple of entries. Spoiler alert, you're looking at those two entries. One of them is a rendering of the Progress Pride flag in 241 bytes, and the other is a rising bubble effect in 31 bytes. Both of these run on the Sinclair ZX Spectrum. The competitions are open to any platform, but I chose the ZX Spectrum. There's nothing too special about them, but they're both good opportunities to talk about the ZX Spectrum and size coding. Two things I enjoy. We'll start with the Pride flag. Let's get into the details. This was my entry to the Tiny Executable Graphics competition, where you need to create a program that produces a static image in 256 bytes or less. At first, this one might not seem impressive. It's just a static picture, right? Anyone could have drawn that. You didn't even do the brown stripe properly. What's wrong with you? Alright, let me explain. First of all, the size. The ZX Spectrum screen is 256 pixels wide by 192 pixels tall, with a really thick border of a single colour all the way around. This flag image fills the whole screen. If you stored this as a standard Windows bitmap, with a colour depth of 8 bits per pixel, you'd need about 48 kilobytes of space just for the image data. Actually, the ZX Spectrum frame buffer is much smaller than that. There's only 48 kilobytes of RAM for the whole machine, so the ZX Spectrum plays some tricks to make the screen buffer smaller. First of all, it only has 15 colours. Well, technically 16, but bright black is the same as black. Furthermore, it only lets you have two distinct colours in each 8x8 cell of pixels, and you have to pick both of them from the bright colours or both of them from the dim colours. You can't mix and match. So actually there's only 48 to 128 different colour combinations depending on how you feel about double counting some of them. The colours for a cell are stored in a byte known as the attribute byte. There is one attribute byte per cell. Unfortunately, that's not enough colours to make the Progress Pride flag. This is why I have to use dither patterns to simulate some of the colours that aren't directly available. This works really well for the orange and purple stripes, and lets me get a nicer shade of blue for the blue stripe. But there isn't a good combination of colours for making a brown dither. I did the best I could with a fairly sparse red dither on a black background. Each cell of 8x8 pixels is represented by one attribute byte for the colour combination and a 1 bit per pixel bitmap. So a cell only takes up 9 bytes in total. There's a grid of 32 by 24 of these cells, so the ZX Spectrum frame buffer format takes up about 7 kilobytes. It's 6,912 bytes to be precise. So if I stored this image as a raw ZX Spectrum frame, it would be 6,912 bytes. The program that I wrote is only 241 bytes long, but generates the full 6,912 bytes frame. That's a really good compression ratio. The program is about 3.5% of the size of the frame that it generates. To show you how it works, I have captured a super slow motion sequence of the execution of the program from start to finish. In fact, I've even captured the startup sequence of the ZX Spectrum. Before we can load up the demo, the Spectrum needs to boot. It normally does this really quickly, but let's enjoy the slow-mo. Part of the boot sequence involves writing data into the frame buffer in reverse, and then erasing it all again. I can split the frame buffer into the two sections to demonstrate how the bitmap appears with just white and black colours on every cell, and show how the attributes are set up by having the same 8x8 bitmap fill every cell. The demo is provided as a .tap file that represents a ZX Spectrum cassette tape with two files on it. The first is a basic program that loads the machine code program and starts running it. There's nothing exciting about it, it just loads the machine code and then jumps to the start of it. The competition allows us to discount the basic loader from our size calculation since it doesn't do any meaningful computation. In slow motion, you can see the load command being typed, the output from the load command, and then the output from the second load command, which is part of the basic loader program. Now we've made it to the start of the demo's machine code program. Let's take a deep dive into how it works. I've split the process up into 6 steps. We'll take a look at how each one affects the frame buffer. The first step might appear strange at first. It clears the screen to a yellow colour then it applies the dither pattern to the first 8 lines of the screen. You can see the dither pattern in the bitmap, but the attributes are set so that every cell is yellow on yellow, so the screen still looks blank for now. If we look at the final image, it's actually only the orange, blue and purple stripes that have this dither pattern on them. So why am I drawing the dither pattern in so many places where I don't need it, and why am I not dithering some places that do need it? Well, that should become clear later on. The ZX Spectrum has some space in the RAM that is designated for custom characters that can be printed with the normal character printing routine found in the ROM. This dither pattern is just a custom character repeated over and over again. The code that puts it here is just a loop that prints the character 256 times. The combination of the load B instruction and the decrement and jump if not 0 instruction forms a very space-efficient loop, only 4 bytes in total for the loop head and tail. The body is also fairly short, only 3 bytes to load the A register with the number of the dither character and then call the ROM's printChar function. It might look like I've set the loop up to do 0 iterations, but actually an initial loop counter of 0 means you'll get 256 iterations. That's the most we can do with a DJNZ loop, and it perfectly fills 8 lines of the screen. It took 8 bytes to clear the screen to yellow, so we've executed 15 bytes so far, and we have this. At this point, the particularly astute among you are wondering, if this is the first thing the program did, then how is the custom character loaded already? An excellent question. I played a fun little trick that I will reveal later, when we get to the appropriate part of the program. I might be building that up a bit too much, it's kind of boring and obvious when you realize what's going on here, but I'm still going to wait to explain it later. Okay, on to step 2. In this step, the attribute data for the thick horizontal stripes is added. There's a lot more going on in this step. It uses 43 bytes of program space to do it, and this includes a 6-byte array that contains attribute values in order. It does this one column at a time, starting at the 10th column and moving rightwards. There's an inner loop which steps down in the Y direction, and an outer loop that steps in the X direction. The inner loop steps to the next attribute value after every 4 steps with the current attribute. Now you can see the effect that is created by the dither pattern bitmap and the attribute data in combination. You can't see the dither pattern on the red stripe because both the filled and unfilled pixels are set to display as red. The orange stripe has 2 different colours, yellow and red, and so the dither pattern is visible. The last 3 stripes don't yet look like the final image. The attributes are correct, but the bitmap data is not correct yet. That will come later. Step 3 is the one that takes up the most program space. It's 68 bytes in total. It uses the string printing function in the ROM to generate the stripes that are at a 45-degree angle. The string that it prints has control characters in it for changing the color attributes while printing. The characters it is printing are a combination of built-in characters and custom characters. The space character and the filled block character are both built into the ROM. The 2 angled half-filled cells are custom characters, as is the dither pattern. There is a function that prints this string 12 times in a row, advancing down and right by 1 space with each iteration. Once the first 12 iterations are done, the program actually modifies itself, changing this decrement instruction into an increment instruction, so that the next time this loop runs, it will move down and to the left instead of down and to the right. It is still printing the exact same string though, and so it really doesn't look right at the moment, but that will be fixed later. It has also introduced some new problems. There's a couple of cells that now have incorrect data in them. Step 4 is purely here to fix up those issues introduced in Step 3. Unfortunately, it takes another 32 bytes to do this. It reprints the dither pattern over the cell that now has the wrong bitmap data, and it fixes the attribute data to get the right colors again. It also doesn't entirely cover the left edge of the stripes, so the left edge of the green stripe is visible slightly. It fixes this too. In the middle there, it did something that's not obvious yet. It stored a number in the space where the basic drawing and printing functions read attributes from. This will be important later. In Step 5, we spend 36 bytes on the most magical part of this whole program. It takes the bitmap from the top half of the screen and mirrors it to the bottom of the screen. This copies the dither pattern into the lower 2 stripes, and fixes the angled stripes too. The result now looks really similar to the final image. The theory of the mirror code is fairly simple, but the details are less simple. In theory, it just needs to copy lines of pixels from the top to the bottom. It should be simple logic. It should just be a loop with 96 iterations, where each one copies one line from the top to the bottom. Unfortunately, it's not quite that simple. It starts with a pointer to the start of the first line and calculates a pointer to the start of the last line, then copies the bitmap data for that line into place. This works fine. Then it moves down by one line and does the same, except why did it skip 7 lines? The first 8 iterations copied these lines, the next 8 copied these ones. This is because of the unusual order of the pixel data in the ZX Spectrum's frame buffer. Mathematically, it's not a problem. The math that calculates the offset from the end, given the offset from the start, is still correct, despite this strange ordering. It's still just a simple subtraction operation. So this isn't a problem, right? Well, the problem becomes obvious when we get to the middle. Let me show you the result that I get if I remove the code that does the special handling of the middle of the screen. Because of the unusual order of the lines, it ends up copying some lines from the lower part of the screen up to the top half of the screen, and thus the effect that the center third of the screen is not correct. The solution to this was to add in some logic that determines if the current offset is below the center line of the screen. If it is, then it will skip that line and continue. This means that the loop actually needs to do 128 iterations. Even though there's only 96 lines to copy, the offset of the 96th line is 128 row lengths past the first byte in the frame buffer. 32 lines get skipped. Now the only thing that's missing is the circle, and that's what happens in step 6. This is where that mystery attribute value from before becomes useful. It was the right attribute value for the circle color. This code uses a fairly sophisticated feature of the ZX Spectrum basic ROM to load some constant values into the calculator stack, and then call the circle drawing routine, which uses the calculator stack values to determine the x and y coordinates and the radius of the circle to draw. The ZX Spectrum ROM calculator is a whole subject in itself, and not one that I'm going to get into here. Think of it like a little DSL inside of the assembly language. It has its own opcodes, which it interprets at runtime in software. The only opcode that I use in this program is the one that stacks a constant value on the calculator stack. This makes the circle drawing step really compact, only 14 bytes to draw the circle. The last 2 bytes of the program are simply a jump to self, so that the program never returns. After the end of the main code path, we find some additional data. First is the list of attribute values for the horizontal stripes, as we saw earlier, then the function for drawing the angled stripes, and the string value that it uses. Okay, now that I've explained all that, what about those custom characters that were magically loaded? Well, those are what comes after everything else in the file, right at the end. The basic loader loads the program at a very specific location, just a little bit before the start of the default user-defined character area in the RAM. The custom characters are loaded into place before the program even starts, simply by carefully choosing where the program starts loading into memory. This was the last optimization that I made, since doing it requires knowing exactly how long the program is, and thus what address to start the program at. Fortunately, the assembler that I use for this project has an assert command that I can use to cause an error if the character data ends up in the wrong place. So that's it. In real time, this process completes in about a second or two, with the slowest part being the circle drawing. But by capturing frames from the emulator much more frequently than the real hardware can display new frames, I'm able to make the super slow motion sequences from this video. I'm quite enjoying watching the image appear in slow motion. What's even more fun, however, is to compare it to a typical game loading screen. Anyone who's used a real ZX Spectrum and had to watch a game load from a tape in real time will be able to tell you just how painfully slow it is. They often would load in an uncompressed splash screen image from the tape before loading the main game data. This took a while to do, so a significant amount of the time you spend waiting for the game was just for the splash screen. Let's watch my image load in real time alongside a popular game from the Spectrum era. What a difference, huh? The second demo I want to talk about is quite different. This was my entry for the 32-byte intro competition. It's a pseudo-random stream of bubbles rising up the screen. So this one is about 1/8 of the size of the flag, and includes animation. This one doesn't do anything particularly surprising, but it's still interesting. I could just walk through the program as it exists in its final form, and explain how it works, like I did for the Pride flag demo, but to do that would mean skipping over some important details about the process I used to develop it. To give you an insight into that process, I'll walk through how it happened. I can do this here because I can actually remember the whole process. First of all, I deliberately set out to write a 32-byte demo, specifically for LoveByte. I didn't have too much of an idea for what I wanted to do, but I thought it might be fun to try and find a way to use the ZX Spectrum ROM's built-in circle drawing function in a tiny demo. As we saw in the previous demo, the circle drawing function can be accessed fairly easily from a machine code program with not too many bytes of code. The first thing that I did was write some code that would draw a circle somewhere on the screen, just to test things out. The ZX Spectrum ROM has been disassembled by various people over the years, and thanks to these efforts, it is well documented where all the functions are in the ROM. So I looked at my favorite disassembly documentation for the ROM and found the address for the circle function. The function uses parameters from the calculator stack. This time I used a slightly different approach to the Pride flag demo. I knew I wanted to be able to move the circles around, so I didn't use hard-coded constants. The circle function takes 3 values from the calculator stack. The first one is the radius of the circle, the second is the y-coordinate, and the third is the x-coordinate. Of course, because this is a stack, we need to push these in the reverse order to the order that they'll be used. Conveniently, there's a function that can put the current value of the A register on the calculator stack, and so I call that function several times to put 3 values on the calculator stack. Testing this out, we find a circle drawn on the screen. Perfect. I can play with the x and y values and the radius value and see how the circle changes. Okay, so I have a circle. Now I want it to move. I've played around with the ZX Spectrum enough to know that there's a ROM routine for scrolling the entire screen up by 8 rows. It's normally used by the print function to move all the text up the screen if there's more to print but you've reached the end of the screen. It works just fine for non-text things too, since it just scrolls the whole bitmap without regard for what's in it. So now I can draw a circle, move the screen up, and then draw another. It's a very simple animation, but it works. Now I want this to be a little more interesting. I don't just want one stream of circles coming from one point and overlapping in the least exciting way possible. I want them to vary in size and displacement. I want the y values to mostly remain the same, somewhere low down on the screen, but I want to vary the x value and the radius. Ideally, I also need them to vary in different ways, so the pattern isn't too predictable and boring. The first thing I try is just adding a displacement with each iteration. I have to store and recall the value of the A register with each iteration, just before pushing the x value. This means that the circle centers slowly drift to the right. This works as expected, but introduces an issue. When the circles reach the end of the screen, it causes an error in the circle drawing routine. The only way to avoid this is to avoid letting the values get too big. If I apply a mask to the result of the addition, then I can effectively do modulo arithmetic on it, so that the x values cycle around this short loop. This isn't very random, however. I want more randomness. If I plot the x value over time, I get a result like this. It's very predictable. I'm able to modify the step size, and this does change the pattern a little, but I want something more chaotic. The change that adds chaos is fairly simple. I just modify the mask value so that sometimes the mask has the effect of decreasing the number instead of just having a modulo effect. I can try a few different values for the mask, but I might change this later once I have the varying radii working. Speaking of which, that's what I did next. I used the same trick. I load the same value from the stack that I was using for the chaotic x motion, and applied another mask value, and an addition to enforce a minimum size. Now I have a bunch of parameters I can tweak. There's the minimum offset in x, the minimum circle radius, and the mask values for creating chaotic patterns in the x and radius. The minimum values are easy to settle on, since they don't interact with other values. The mask values are more of an art than a science, but I settled on these values, which I think create a nice pattern. There's 2 clear groupings that the animation switches between, but it takes long enough to repeat the exact same group of circles that it looks suitably random. So now let's have a look at the file size. That's too big. I need to remove a few bytes. This is where I got a little bit lucky. The first thing I did was rearrange some things so I don't have to initialize the A register at the start of the program. Instead, I pop some value from the stack, which now becomes a kind of random seed for the visualization. This does technically cause the stack to be corrupt, but that doesn't actually matter since this would only be a problem if I wanted to return control to the basic interpreter, which I don't. Now I still need to lose some bytes. Perhaps I'll have to compromise on something else. After all, the competition category is for 32-byte demos. I can't afford these bytes. Let's see what happens when I remove this assignment to A. The code that pushes the value of A onto the calculator stack actually consumes the value of A and leaves something else in its place. I'm not sure what value exactly, but maybe the value it leaves is close enough to what I want. Yeah, that works. There's always a slight risk with an optimization like that. The risk is that this value depends on something unpredictable, and you might get a very different effect to the one you intended. Regardless, this works fine every time I've tested it, with a few different timings, so I was happy enough to submit this to the competition. It was only after writing this that I realized, hey, these look like bubbles. And so I decided that these are bubbles, hence the name of the demo. Despite being some of the smallest demos I have submitted to any demo competition, these are the demos that I've enjoyed working on more than any other I've done previously. Thanks for watching. I hope you enjoyed. You can subscribe if you want to see more videos like this. Maybe even send me a super thanks if you're feeling generous.